That you did. I'm going to go get a couple things ready, including this. There we go. Much better. And I'll be back for 10:10. Stop. What's the problem? It's not here actually, it's still up there. Oh. I never brought it in last night. am adding a link into the description. If you refresh the page, I believe that link should now be live in the description. Near the last main part of this lesson, during the last main part of this lesson, I will be referring to that website. Yes. Excellent. All right. So, what is that? Let's get started. Today is the 27th. And this, well, for lack of a better term, I'm going to give this actually two titles from what I wrote in my notes. Bring that over here. There we go. I am going to call this Confidence Intervals and Hypothesis Testing, or, quote, how, if I could spell how today, how can a normal curve help? So the official title is Confidence Intervals and Hypothesis Testing. But I'm also putting into quotes this idea, how can a normal curve help? And that's what we're mainly going to be focusing on today. So I'm going to outline an example of two athletes, athlete A and athlete B. And they are competing, these two athletes, they are competing in athletic competitions. Two specific events. They are going to be competing in the long jump, and they are going to be competing in the shot put. So, long jump, shot put. Athlete A versus athlete B. Now, the main question for this example is, who is the better athlete? Is it athlete A or is it athlete B? Well, in the long jump, athlete A jumped 6.78 meters, and athlete B jumped 6.30 meters. Clearly, athlete A is the better long jumper than athlete B. Athlete A is the better long jumper. But then they go over to the shot put. And athlete A threw the shot put 14.77 meters. And athlete B threw the shot put 16.40 meters. Clearly, athlete B is the better shot putter. The question is now, who is the better athlete? I see you in the chat, Kyle. I see you saying athlete B. What is your justification behind that? You started typing that before I even finished the example. Who is the better athlete? Okay, if you say so, let's see what happens. Now, one might argue that athlete A jumped a distance smaller than that difference-wise than athlete B did for the shot put. For example, athlete A, well, Mr. Markey, athlete A clearly only jumped 0.48 meters farther, but athlete B threw the shot put 1.63 meters farther. So here's the problem. There's an old adage comparing apples and oranges. That's exactly what this is. This is comparing apples and oranges. And you cannot compare apples and oranges because they're two different types of fruit. They have two different types of tastes. They have two different types of texture. They have everything. You cannot compare apples and oranges. Who's to say what type of athletic ability is needed to compete in the long jump versus the type of athletic ability that is needed to compete in the shot put? Long jumpers tend to be faster, leaner. Shot putters tend to be stronger, bulkier. Who is the better athlete is a bit of a conundrum in this case. Okay, Kyle, if you say so. So I want to introduce a few other pieces of information before I go about trying to answer this question, who is the better athlete? At the particular competition, at the competition that these two athletes competed in, the average long jump, now, Kyle, I don't think that oranges are better. I'm just simply stating a fact. The idea of comparing apples and oranges, you cannot do that. You cannot say that one is better than the other when they have two competing qualities. Anyway, the average long jump on that particular day amongst all of the athletes was 6.16 meters, meaning that both athlete A and B were better than average. They were both better than average. In fact, the average shot put of the day was 13.29 meters. They were both better than average. Now, there is another measure that I'm going to bring in here, standard deviation. Mu is referred to as the mean, and this sigma, this lowercase sigma, is referred to as the standard deviation. So, the reason why we need the standard deviation will become prevalent a bit later on, but let me just write it out here. Standard deviation for the long jump was approximately 0.23 meters, and the standard deviation for the shot put was 1.24 meters. Meaning, on average, every athlete deviated from the mean by about 0.23 meters on average. Now, these two athletes, athlete A and B, clearly, athlete A is definitely way above average in that case, but 0.23 meters is where it's at. 1.24 meters on average, every athlete at this competition deviated from the mean by an average of about 1.24 meters. That's the idea of standard deviation. So, how does this help us? How do we compare the two athletes? Who is the better athlete? Well, it comes down to a few statements here. We need a standardized ruler for measuring. Meaning, if I'm measuring in kilometers and you're measuring in miles, we need a conversion. You either convert the kilometers to miles or miles to kilometers so that we're both using the same measurement. That is important. I could be measuring in pounds and you could be measuring in kilograms. They're not the same unit. You cannot compare the two of them until you have this standardized ruler for measuring. In statistics, there is a standardized way of measuring data. When data is normally distributed, and I'll show you what normally distributed means in a moment. But when your data is normally distributed, we can compare data points using what is known as z-scores. There is this concept in statistics known as z-scores, and it basically converts data into a standardized measurement of z-scores so that you can actually compare the two of them. Now, just for the sake of argument, a normal curve typically looks like this. A normal curve is a bell-shaped curve. It is symmetrical on both sides. I'm going to be continually referring to the normal curve throughout the course of this lesson, simply because that's what it comes into play. I think even the title that I gave it, how can a normal curve help? Well, when the data is normally distributed, which in this case we're going to assume it is, we can compare data points using z-scores. How do you calculate a z-score? Like that. You calculate a z-score by finding the difference between the data point and the average and dividing by the standard deviations. In fact, a z-score is the number of standard deviations above or below the mean a data point is. A z-score is the number of standard deviation above or below the mean a data point is. That's what a z-score is. So, for example, if I'm going to go back to our athletes, I can do some calculations for athlete A and athlete B in comparison to the events that they competed in. And I will write this little formula over here so that I have it. The data point minus the mu over the standard deviation. So, if I'm looking at someone like athlete A, athlete A in the long jump, let's just compare long jump. Athlete A's data point was 6.78, the average was 6.16, and the standard deviation was 0.23. If I were to do this calculation, boom, approximately 2.7. Meaning, athlete A, their long jump score, their long jump distance of 6.78, was approximately 2.7 standard deviations above the mean. Z-scores can be positive or negative. If they happen to be negative, then the data point fell below the mean, meaning you were below average. If it's positive, it means you were above average. The larger the number, obviously, the better off you are compared to everyone else. Athlete A, in the shot put, their distance was 14.77 minus the average divided by the standard deviation. 14.77 minus 13.29 divided by 1.24, 1.19. Yeah, 1.19, I could do that, because it was 2.70 for the other one. That was athlete A. Athlete A was 2.7 standard deviations above the mean for the long jump, and 1.19 standard deviation above the mean for the shot put. Let's look at athlete B. Athlete B, for the long jump, they jumped 6.3 meters minus the average. Now, obviously, they did not jump as far as athlete A, so they would have a smaller z-score. They have a z-score of approximately 0.61. Whereas for the shot put, athlete B threw 16.40 meters minus the average divided by the standard deviation. I'm going to put that in parentheses. Boom. 2.51. So, what does this mean? We knew already that if you compared the two athletes for the long jump, athlete A was better. We knew that. When you compared the two athletes for the shot put, athlete B was better. Yes. But who is the better athlete overall? Something that you're allowed to do if you add the two z-scores together. I can spell total today. Total z for athlete A was 3.89. Athlete A was a combined 3.89 standard deviations above the mean in terms of the two events that they competed in. Athlete B was only 3.12 standard deviations above the mean. Now, anybody who is watching this video after the fact can see all of the comments that Kyle has put into the chat. He says, it's B. Athlete B is better. I'm an athlete B fan. Athlete A is dumb. Athlete B is better. Athlete B for the win. Well, guess what? Athlete A is better athlete on average. It's because if you have that standardized measurement of a z-score based on a normal curve, you can see that athlete A has the higher combined total z-score. It has to do, the reason for that has to do with how much better they are on average compared to everybody else. For example, athlete A right here, because of the mean and standard deviation of everybody else, athlete A was 2.7 standard deviations above the mean, whereas athlete B was 1.19, I'm sorry, 0.61, only 0.61, less than a standard deviation above the mean. Yes, athlete A is better on average, but not by that much. And then both of them were considerably better than the average for shot put. Yes, athlete B was like 2.51 or something like that, but athlete A was 1.19. So athlete A, on average, was much better than the average compared to athlete B. It's a strange thing, but that's how we are allowed to compare apples and oranges. If you have data that is normally distributed, you can then convert things to a z-score. So, put these in a safe spot. A couple of pieces of information. Hopefully when Kyle gets back, I'll be able to rub it in his face. Kyle, are you back? I can't tell. Anyway, a couple of pieces of information. Put a little bullet point here. Typically, a data point is, quote, unusual, if it's more than 2 standard deviations away from the mean. Meaning, if you have a z-score that is either greater than 2 standard deviations or less than negative 2 standard deviations, meaning, like, hold on, I'll draw it like this. Here, it's better if you see it visually. Here's the normal curve. This would be z-scores along the bottom. A z-score of 0 means you're right on average. Z-score of 1, z-score of 2, meaning you're above average. Z-score of -1, z-score of -2, meaning you're below average. If you are more than 2 standard deviations or less than -2 standard deviations away from the mean, you are considered an unusual data point. That's the way these normal curves typically help you out when comparing these things. Again, A z-score is calculated with the data point minus the average, basically the difference between the two, divided by the standard deviation, and it is the number of standard deviations away from the mean that you are. Now, this wasn't the title of this particular lesson. The title of this particular lesson had to do with confidence intervals and hypothesis testing. So let's jump into that and see why I spent all that time talking about z-scores and normal curves, because that is what this whole thing typically becomes about. Let's talk confidence intervals. Confidence intervals are constructed in an attempt to capture the true mean of a population. And you'll see how this actually relates to something that you've probably already learned about in the past, but I'm going to save that as a surprise for a moment. Confidence intervals are constructed in an attempt to capture the true mean of a population. Now, it is next to impossible to actually know the true mean of a population. If you wanted to know the average height of every single person living in America today, adults and children, whatever, you would have to find the height of you'd have to take a census of every single one. That is impossible. You're not going to get every single one. You're going to spend all your money. Can't do it. If you wanted to find the opinion of, let's say, a political candidate's approval rating or something like that, you would have to get the opinion of every single person in America and then average them together on a scale of like 1 to 10 or something like that. I don't know. But that's impossible. By the time that you finish, people's opinions may have changed. You may miss people. You may not have the resources and money to get it all if you had to hire people to do it for you. So, instead, we attempt to capture the true proportion based on a sample that is taken. So, just as a side note, for our confidence intervals, it is what we call a point estimate. Emphasis on the word estimate. It is a point estimate of a population parameter. Let me give you an example. We want to know the approval rating, say like out of 100% or something like that. I don't know. The approval rating of the president. We can't sample the whole US. Can't do it. So we take a small sample. When I say small, like maybe like a couple hundred people or something like that. Doesn't really matter. A small sample. And estimate a range for what the true mean would be. This is the idea of a confidence interval. We want to know the true mean of something for an entire population. Unfortunately, we can't sample the whole population. So we take a sample. And based on that sample, we can construct a range in which we are hopeful that the true mean is within that range, that it is captured by that range. Kyle, you're back. Guess what? You can go and watch the video back later if you want. But athlete A was better. Athlete A was the better athlete. So, that's all I got to say about that. Oh, goodness gracious. Let me give you the formula for confidence intervals and talk about what each of this means. So how does one actually construct a confidence interval? A formula for, and I'm not going to write it out, just confidence interval, I'm just going to abbreviate it, for means is the following calculation. There we go. Now, a couple things to this. I teach AP statistics. And this formula, if I were teaching it for AP statistics, would technically be wrong. Teaching AP statistics, there is a huge difference between having a population standard deviation and having a sample standard deviation. I'm not going to go into those details. This is Algebra 2. I am teaching this the way that the textbook teaches this. So, disclaimer, I don't agree with this formula, but for the purposes of Algebra 2, this is unfortunately what we're going to use. And that's what I'm going to stick to. Now, first of all, yes, that z is referring to the normal curve that we talked about before, and it has to do with the number of standard deviations away from the mean that we are. Yes. That is why I had to spend the time talking about that. X bar and S, based on our previous lesson, X bar and S are based on the sample. X bar is the sample mean, S is the sample standard deviation, and N is the sample size. So just as a side note, N is sample size, X bar is sample mean, S is sample standard deviation, and the Z is the value that corresponds to percent confidence, which I'm going to talk about in a moment. Basically, for a confidence interval, we will never be 100% confident. I reference back to the previous page of notes. The previous page of notes talked about the idea that we are attempting to capture a population proportion, or I'm sorry, a population mean. We are attempting to capture something about the population. However, we are only attempting. If you say so, Kyle. But statistically speaking, we will never be 100% confident about anything. Ever. If you try to run a confidence interval in the calculator using some of the things that I do, can't do it. You can't do it. Typically, we use confidence intervals of 90%, 95%, or 99%. That's what we typically use. Now I'll show you the example for 95, and then I'll give you the numbers for the rest. The idea is that, well, the population's normally distributed. And we are hoping that the interval that we found is capturing the middle 95%, but there's no guarantee that it did. Samples are, of course, random, and they could differ from one another. I can construct the 95% confidence interval. Someone else can, a fifth person, a sixth person, it doesn't matter. But all these intervals might be slightly different from each other. We are simply looking at trying to capture this 95% confidence interval. And if we're talking z-scores, yes, I know, seventh person. If you're talking z-scores like we did before, this 95% confidence interval should be from negative 1.96 z-scores to positive 1.96 z-scores, approximately. That has to do with that unusually high and usually low thing of -2, +2, but these are more accurate numbers. In fact, the z value that you're going to use for 90% is going to be plus or minus 1.645. For 95%, it's going to be plus or minus 1.96. And for 99%, it's going to be plus or minus 2.576. If you were taking AP statistics, these numbers wouldn't typically be given to you. You would have to calculate these numbers. Yeah, but these are the numbers that are given to us. You don't have to worry about plus or minus because the plus or minus is already taken care of in the formula. I'm going to show you how to use that formula in the next example that I have. But these numbers we're going to use. And then I have to talk to you about interpreting a confidence interval, but we'll talk about that in a minute. Here's an example. Example. 200 students are surveyed. On the number of minutes they spend studying / doing homework, let's just say. Studying and homework combined. The average for the sample was 52.5 minutes, if I could write that correctly. And the standard deviation for the sample was 5.1 minutes. Of course, like we said, the sample size was 200, and I want to construct a 95% confidence interval using this data. Now again, disclaimer, if I were teaching AP statistics, I would not be teaching you how to do this particular formula. I would be teaching what is known as a t-interval, but this is Algebra 2, and I'm sticking to what the textbook is suggesting. Whatever, Kyle. I am a math teacher, not a grammar teacher. There you go. Back to the formula. The formula was x bar plus or minus z times s over the square root of n. Now, that would be 52.5 plus or minus, going back to the previous number, should be with the 95% confidence interval, it should be 1.96 times 5.1 over the square root of 200. This becomes 52.5 plus or minus. Let's see what this calculation does. Oh, forgot a 0. There we go. 0.707. So, to construct this interval, we would have to add 0.707 and subtract 0.707 from that number. Now, I want to point something out about this. Just this portion of the formula right here, before I finish the calculation. This portion of the formula is known as margin of error. A lot of people have heard that phrase, margin of error. And they have their own opinions and thoughts as to what margin of error is defined to be. Well, they would be wrong. A margin of error, the purpose of it is to construct a confidence interval. And a confidence interval is attempting to capture the true mean. A margin of error is not saying that the true mean is within that interval. It's just saying that you are a certain percent confident that you are within that interval. It is the error of margin. You're the error of margin. Anyway, back to this. And I'll give a few interpretations of this. 52.5 plus 0.707, 52.5 minus 0.707. This interval would be 51.793 to 53.207. Now, what that means is this. What? Whatever. What that means is this. We are 95% confident the true mean number of minutes spent studying or on homework is within this interval. We are 95% confident the true mean number of minutes spent studying / homework is within this interval. We're not 100% confident. We will never be 100% confident. If you tried to be 100% confident, the entire thing would fall apart. Can't do it. The reason being is because of that normal curve. If you say you're 95% confident, you can actually calculate what those z-scores would be. But if you were 100% confident, you would have to extend that percentage infinitely in each direction. And since you can't do that, there's no such value that you can put in for z for 100%. You can't do 100%. You have to do something less than 100%. He's still going on and on and on about Minecraft, I'm assuming. Anyway, back to this. Now again, we're not saying that we have captured the true mean. We're just saying that we're 95% confident that we've captured the true mean. In a different sense, it's like if 1,000 people did the exact same survey, but different surveys. If like 1,000 different surveys were done and 1,000 different intervals were constructed, 95% of them would capture the true mean and 5% would not. We are simply hoping that we are in the 95%. It's not a guarantee. That's why we're saying we're 95% confident and not 100. Now that leads into the last thing that I want to talk about today. The last thing that I want to talk about today is a hypothesis test. Kyle, I don't even know what you're saying. Anyway, back to this. So, first of all, a confidence interval, as I said before, is an estimate Kyle, are you about to tell me that it's Shia LaBeouf? Yeah, you totally are. Anyway, a confidence interval is an estimate of the population mean. It's an estimate of the population mean. But now, I want to talk about a hypothesis test. A hypothesis test is used to assess a specific claim about the mean. Let me give you an example, and then I'm going to go into the details as to what to do about that. So let's just say a school administrator, school admin, believes his school is faster at evacuations than the state mandated 3 minutes. The state mandates that every school needs to be able to evacuate in 3 minutes. And a school administrator believes that his school is faster than that 3-minute benchmark. In fact, after 10 test evacuations, let's say they do one, a drill once a month. After 10, the school average is 2.5 minutes with a standard deviation of 0.9 minutes. Clearly, the school average is faster than the state mandate. But here's the question. Does the admin have statistically significant evidence that his school is faster? Question mark. The school administrator only took a sample of 10. And yes, his average was faster. But is that the result of random chance? Or is this the result of his school actually being faster on average? This is what a hypothesis test is used for. It's used to assess a claim about the mean. The school administrator is claiming that his school is faster, or less than 3 minutes on average. How do we go about that? Well, we go about that once again with the normal curve and with z-scores. There is a general idea, and I'm going to put that information there because I'm going to need it in a moment. There is a general idea of a sample distribution. That is shaped like the normal curve with the claim of 3 minutes being right in the middle. And each of these little dots, or dot lines I should say, represent a certain number of standard deviations away from the mean. Now, a standard deviation of a sample would actually have to be calculated like this. You would actually have to divide it by the square root of n. That harkens back to the confidence interval sample that we just talked about before. Now, if you did that for this particular example, again, I put x bar at 2.5, I put s at 0.9, and n is at 10, because he took 10 test evacuations. 0.9 over the square root of 10 would put you at approximately 0.285. Meaning that on this normal curve, if I were to do 3 minus 0.285 minus 0.285, the school's sample mean is right here. So what this basically means is, yes, the school was a certain number of standard deviations below the mean. or a certain number of standard deviations below the claim, I should say. Now, what we're going to do is we're actually going to calculate the chance of that happening. And this has to do with something called a normal CDF. Now, for the sake of time, I'm going to show you how to do it on the calculator and where it is on the calculator. In fact, let me just show you real quick so you know exactly what I'm working with. But if on the graphing calculator, and you have these on the 83s, you have these on the 84s, if you hit second vars, you have something known as normal CDF. Now, for the assessments that I am going to give Algebra 2, I am not going to expect that you are going to use normal CDF because I cannot expect that everyone has a graphing calculator at home. And because of that, my assessments are going to be a bit more straightforward than this. You'll see. They're going to be a lot easier than you actually having to calculate these things by hand. But normal CDF, again, second vars, there's the normal CDF, the thing that we need. That refers to the normal curve. It's actually the cumulative distribution function. That's what the CDF stands for, but that's besides the point. But what we're going to try and find out is what is the probability of getting that x bar, assuming the population mu is true. Assuming that 3 minutes, the population mu, is a true statement, what are the chances that that principal would get that x bar, that 2.5 minutes, based on the number of samples that he did? The way that we do that is like this. Now I'm going to do this twice here. Lower limit, upper limit, mu, and then the standard deviation over the square root of n. Kyle, I've stopped listening to your lyrics. I'm just going to keep going with my lesson here. Now, when I say lower limit, upper limit, I am referring to what I just drew over here. The principal is claiming that his 2.5 minutes is less than the claim of 3 minutes on average. The lower limit, upper limit, well, this would technically be like negative infinity, or just some, negative 10,000 or some junk like that, whatever you want to put in there. Negative small number, whatever. Comma 2.5, which is the claim of the principal. There's the claimed mu. And there's 0.9 over the square root of 10, which we calculated before. If I were going to do normal CDF, I can't type in negative infinity, so I'm just going to put in like negative 100,000, negative 10,000. Comma 2.5, that's my lower limit, my upper limit, my mean, and my standard deviation. I get approximately 0.039, which means, now again, going back to my question here, what is the probability of getting 2.5 minutes, assuming that the 3 minutes on average is true? Assuming that the school actually does average 3 minutes, assuming that nothing is going on, assuming that the school is no better than the state claim, what are the chances that they would get an average of 2.5 given that number of trials? And yes, it's about 4%. There's about a 4% chance. Now, this is the beauty of everything that we're doing today, and I'm gonna wrap up with this question, of course, but there's a lot of extra information that I want to give on top of it. When it comes to hypothesis testing, there is what we call the null hypothesis, and there's what we call the alternate hypothesis. Now, the null hypothesis in this case was 3 minutes. There's nothing going on. There's nothing out of the ordinary. Kyle, I'll talk about that after I finish the example. Remind me when I'm done. And the alternate hypothesis is, well, you know what? The principal claims that they're better. The principal claims that they are better than 3 minutes. Okay? Well, what evidence do we have? Well, the evidence that we have is, well, he found an x-bar of 2.5, a standard deviation of 0.9 out of a sample size of 10. Okay. What does that evidence show us? Well, the chance of getting that evidence, assuming null is true, the chance of getting that evidence, assuming that the null is true, is approximately 3.9%. This is what is known as a p-value. It's a technical statistical term that they call a p-value, the chance of that happening. Well, if the p-value is smaller than what we call the alpha level, which is typically 5%, then we have evidence against the null hypothesis. This is an important concept that I'm going to spend a little bit of time on right now, verbally. The p-value is 3.9%. If the p-value is smaller than alpha, which typically is 5%, which it is, then we have evidence against the null hypothesis. I want you to think of a court of law. Think about someone being put on trial for murder. When that person is on trial, they are assumed innocent. They begin assumed innocent. Now, in this case, the 3-minute population parameter, we're assuming innocent. We're assuming nothing's going on. We're assuming nothing out of the ordinary. Then, evidence is presented against innocence. Spell innocence today. Whatever. Innocence. Innocent. Whatever. Innocent. Evidence is presented. Then what happens? Then a jury digests that evidence, and then they determine whether or not they're going to vote guilty or not guilty. Then, guilty or not guilty. I want you to notice this for a second. All right, innocence is right. You're assumed innocent. Then evidence is presented against your innocence. But then, in a court of law, they never proclaim you innocent. Even though you are assumed innocent at the beginning, they never proclaim you innocent in the end. They never do. At the end of a trial, you are either proclaimed guilty or not guilty. Only. That's it. I mean, obviously, mistrial, whatever, I don't care. But you're either proclaimed guilty or not guilty. Now, in the same sense of guilty or not guilty, guilty would be what we call rejecting the null, or rejecting the innocence of the problem, or the innocence of nothing happening. By the way, you see assumed innocence, that's what the null hypothesis is. And if you reject the null, if you proclaim it guilty, then you have evidence against the null hypothesis. Whereas, if you presume not guilty, then you fail to reject the null. That would be not guilty. That would be, we don't have enough evidence to show that the null hypothesis is wrong. And that would be the particular, I'm going to write that conclusion out in a minute for this problem for the school administrator. This is a very important concept. And it has to do with whether or not the p-value is less than that 5% level, that 5% threshold. I want to write the conclusion to this school administrator problem, and then I'll wrap up with a couple thoughts. So, because the p-value of 0.039 is less than the alpha, which in this case is 5%, we reject the null hypothesis of 3 minutes. There is evidence to suggest the school's average evacuation time is less than 3 minutes. This is a proper conclusion to the problem. We calculate a p-value, which in the case of my assessments for Algebra 2, I would typically give you the p-value. You would get a p-value, you would determine if it's low enough. If the p-value is low enough, then you are allowed to reject the null hypothesis. If the p-value is not low enough, you would have to fail to reject, meaning you don't have enough evidence to suggest that. In fact, let me just write a kind of a dichotomy right here. If p-value is less than 0.05, we reject the null. Evidence to suggest claim, which the claim being made by the principal or school administrator, whatever you want to call them. If the p-value is greater than 0.05, we fail to reject the null. Not enough evidence to suggest claim. Rejecting the null would be a guilty verdict. Failing to reject the null would be a not guilty verdict. This has everything to do with a court of law. Not innocent, right? I'm sure. But that's what this thing has to do. Again, typically for the assessments that I'm going to give you, a lot of this is going to come down to the conclusion, the proper wording of things. I'm probably going to do some practice worksheets or something like this, like multiple choice things, and eventually there will be an assessment on this information as well. So I'll probably do another video maybe before the end of this week, maybe early next week. I haven't decided yet. But this is the Algebra 2 introduction to confidence intervals and hypothesis testing. This would officially end the lesson. So, Kyle, I wanted to talk very briefly about my plan for the rest of today being Tuesday, May 27th. I am going to be on, again, live streaming at 1 o'clock for my discrete math class. I'm going to be teaching sequences and series. And I really enjoy sequences and series. But again, that's discrete math. You know, you don't have to show up for that, but that's what I'm going to be doing. Wait, today's Wednesday? Oh my gosh, today's Wednesday. Look at me. I have no idea what day it is. Okay, fine. Wednesday, May 27th. Whatever. But yeah, I'm going to be streaming today at 1 o'clock for my discrete math class. So I am going to be streaming there. Yeah, that's probably what messed me up. Anyway, I will actually be uploading a video game video today at some point of me running Super Mario Brothers. Last night, I successfully ran it in under 5.5 minutes, and I'm going to be submitting that run to speedrun.com. So I'm going to be uploading that 5.5 minute video or so. And we'll see if it gets accepted. If it gets accepted, I think I would be like in the top 600 all time, top 600 all time of people who ran this game. So we'll see what happens. I would love to get my time a lot faster, which I think I can, but I will be posting that video probably within the next couple hours or something like that. I haven't decided. But anyway, that's it for me for now. Thanks for joining. And I'll be back on at 1 o'clock for discrete math. See y'all later. Oh, if I can actually click the thing to stop this.